Hi, welcome to StatStuff. I'm Matt Hansen. Well, if you ever want to impress your friends at how smart you are, nothing does it better than throwing around the word multicollinearity. For such a complex sounding word, it's actually a very simple concept. So in this lesson, we'll define what multicollinearity means and how it's an essential part of finalizing our transfer function. This lesson presumes that you're already familiar with many of the hypothesis tests that we reviewed in the analyze phase. So if you haven't reviewed those yet, then it may help you to do so before viewing this one. But for now, let's begin this lesson with defining what the transfer function is again.
Well, we need hypothesis testing because, remember, our goal for the project is to resolve the problem by first building a transfer function. We don't want to just alleviate the symptoms that we're seeing, but we want to get to the root cause. You may recall my example of my daughter Hannah. We don't want to just alleviate the arthritis pain that she was feeling in her leg, but we want to heal the root cause, which was the strep throat. So if we don't know what the root cause is, then that means we need to build a transfer function to figure that out. By building the transfer function, we can know what changes, that is, what improvements that we need to make that should fix that root cause. Now, if you recall, the transfer function is defined as y equals f of x. That is, the output response of y is a function of one or more input x's. It's part of the IPO flow model, again, that we described before in the IPO flow model, where we have an input that leads to a process and an output. Well, the y refers to that output. The process piece refers to the function that's applied to an x, the x being the inputs that are part of it. So it's really expressed in the IPO flow model to an equation. Now, how does this transfer function fit with hypothesis testing? Well, hypothesis testing tells us which of those x's, which of those inputs that we're looking at, are independently influencing the y, the output metric. When we reject a null hypothesis, we're building evidence proving which x's are guilty of driving the y. And what we'll do at the end is we'll compile all the evidence in the improve phase of DMAIC, and that's when we'll begin to fix those root causes or come up with a plan that's going to fix those root causes. Now that we know from the hypothesis testing which of the x's are the most critical x's that have the most influence and where we need to make the biggest changes that are going to affect our output y.
Okay, now let's get to the exciting part of defining this $64,000 word, multicollinearity.
Well, multicollinearity really refers to an interdependency between the factors that we're evaluating. So as an example, when we're building the transfer function, we're going to expect that each of the x's, that is the inputs into our transfer function, that each of those x's are going to be independent. Because if they're not independent of each other, then it could mean that there's not accurate control of those inputs in order to create the desired output, or that y. Well, multicollinearity, again, is when there's two or more of those independent variables that are found to have an interdependency. They're not exclusively independent of each other, but there is some relationship between these x values or the inputs where we're expecting or hoping for independence. So let me go through an example of one of those. Let's say we have a transfer function where fuel efficiency is our primary output, or our y. That's what we're trying to aim for. We're trying to improve, or at least measure in this case, fuel efficiency for a vehicle. Well, that is, we would say that would be the output y. The inputs, we would say, would be like fuel price, the speed that we're driving on a regular basis, or engine size, or the vehicle weight, or those sorts of things. Well, in this case, we would say engine size and vehicle weight are considered to be independent factors that each influence fuel efficiency, as well as any of these other factors that we might identify. So in that way, they're all independent because they all have some effect on fuel efficiency, or they have some relationship to it, but it's not exclusively independent, because the bigger the engine that you have, the bigger the size of the engine, then the more that also adds to the weight of the vehicle. So there's actually a relationship between at least these two variables, engine size and vehicle weight, and that's kind of an example of what we mean by multicollinearity, that again, they can each separately have some sort of influence on fuel efficiency, but there is some relationship between the two of them together. And because there's some relationship, we can't treat them as exclusively and independent of each other. We need to at least understand the relationship and the effect they have on one another, as well as the effect they have on the overall output y. Because if we just make one change to one of these factors that we might think is a critical factor, yes, it might have the desired output that we're looking for overall metric or output y, y, but at the same time we could be having a negative effect or some other repercussion effect on some other factor that we may not have intended. So how are we going to test for multicollinearity? Well, this is where we're going to use multiple regression procedures in order to test for that. So these procedures really consist of 7 general steps. They're going to be using several tools like correlation testing, matrix plots, and regressions, and that sort of thing. So we're going to break out those steps over the next sets of slides that we're going to view together.
All right, now let's go through all 7 of the steps that make up the multiple regression procedures.
All right, before we begin actually running through the multiple regression procedures, I want to go over just a few assumptions we need to at least understand up front before we begin. First of all, we need to assume, or at least understand, if the output y is normal. Now we can validate this by looking at a normality test or probability plot and look for the p-value from that test. If the p-value is greater than 0.05, which is traditionally the default value we would assign for like the alpha risk level, then we can say that the distribution is normal, and so because of it's normal, then we can move on with these procedures. But if the data is not normal, then consider transforming the data in some way to make it normal, like through Box-Cox transformation, or you might have to go forward just assuming that there's some sort of risk now because you're dealing with non-normal data. It could have an effect on the results. So just be aware, if you're not going to transform your data in some other way to make it normal, just be aware that you may need to go forward with some sort of risk that could be affecting your data results because it's non-normal. Now, another assumption is that we need to understand that the correct sample size is being used for this. Now, you can use a sample size calculator on the data to ensure that you have enough data points in your analysis. Also, we need to make sure that each of the x's that we're testing within these multiple regression procedures are continuous. Now, just because we say that they are continuous, there are some ways that some folks try to fool Minitab or whatever statistical software that we're using to fake it as if it's continuous. For example, if you have a discrete value where the results are yes or no, you might use a 1 to represent the yeses and the 0 to represent no. And when you're using a 1 or a 0, then the statistical tool will consider it to be continuous value because it's numeric. It doesn't know any better. But we know better, and we know that it's actually a discrete value that you're fooling the system to allow it to work. Well, that might be appropriate to get it going through. I would say that that might be okay to do in some instances if you consider that discrete variable to be something worth including in these procedures, but not necessarily a critical factor. So in that case, it might be okay to include that in here, but just be aware that that's not the ideal method, and it may be best just to exclude those types of discrete values altogether when you run it through these types of procedures. So, having said all that, let's start with step number 1 among the procedures. The first thing is you need to test each of those x's that we're looking at. Again, as we try to understand what's a part of our transfer function, we need to test each of those x's against the y to ensure that there's some sort of relationship to some degree on there. Now, we should have already been doing this in the analyze phase. At this point, again, we're saying that we're in the improve phase. So we should have already had all those continuous value x's tested against the y either through a multiple regression or separate correlation test, and that's where you would have looked for something like a high R-squared adjusted value or a high Pearson correlation, whichever one you're going to use. But if you see that there is a strong enough correlation between them, then that's the first step we want to look for. If there's not a relationship that we can prove using those kinds of tests, then those are probably factors we need to exclude from these types of procedures as we move forward.
Okay, now for the second step, we'll run a matrix plot for all the x's and the y.
Well, in the second step, we're going to run a matrix plot against all the x's and the y. Now, this is where you go, like in Minitab, you go to the graph menu and select matrix plot. And from there, we would check all the linear relationships for possible collinearity between them. So here's an example of the output you would get when you run the matrix plot for all the variables. And this is the example that we've been using all along in the Minitab sample data file that's provided on the website. So in this case, we'll say like metric A is our primary y. In this case, with the plot, we're comparing it to these other continuous values like metric B, C, metric D, and metric E as well. Now, the way this is drawn is actually, it's kind of like a matrix in the sense that this illustration here is showing the correlation between metrics A and B. This one here is between metric A and metric C. This one beneath it is metric B and C, and so on. But if you notice, this one is also the same thing as like metric B and C over here. So these two are actually the same. This one over here in the left-hand side is actually the same as this one up here, and so on. So it's really kind of like a mirror image to some degree of some of these. Now, it may look like they're exact duplicates, but they're actually a little bit reversed depending on which one's going to be on the y-axis or which one's going to be on the x-axis and how it's plotted. So you'll notice this example here of metric C and D that's being compared is the same one here between metric C and metric D. Well, if you notice that this line here is filled up more, and this shows as the upper one versus this is the lower one. It really doesn't matter which one you're referring to. It just one might visually stand out to you more when it's one image versus if you reverse the axes and then you look at it, how it's displayed in a different perspective, it might stand out to you differently. In this kind of example, what we're going to be doing is looking over each of these images, and we're going to be looking for some sort of relationship. So similar to what we've done in step 1 to look for a relationship, this is just another way to look for it, but we're also going to go a step further and looking for some sort of multicollinearity between some of the factors. So in this example here, we would see that there is some sort of relationship between metric A and at least metric C, D, and E that are being compared here, because we're seeing some line that can be drawn, and it looks like a very strong relationship with many of these. However, we would see down here that there could be some multicollinearity between metric C, D, and E. Again, this is because metric A we're saying is our y, metrics C, D, and E are actually x factors. And because we can see some relationship among them, that's going to suggest to us that there probably is some multicollinearity between them. So based on this example, we would say that we need to dig a little bit further to at least metrics C, D, and E to see if one or more of them needs to be excluded because of some interdependency or interrelationship between them.
Now in step 3, we'll run a correlation matrix on all the x's and the y.
All right, now in step 3, we're going to be running a correlation matrix again on all those x's, the continuous values, and our continuous y. So like we've done before in the analyze phase, this is where you go to mini tab, and in that you go to the stat menu, select basic statistics, and choose correlation. And in there we select all the values that we want to have compared, and what we're going to be looking for is a low p-value as well as a high r-squared value, or really it's an r value that's being shown on here, which is the Pearson correlation. So according to this, what we're going to do is we're going to have an output that looks something like this if we're again looking at the same 5 different metrics in our sample data file. And what we're going to be looking for here is again metric A that we're comparing to metric C, D, and E, where the lower number within each of these different groups of numbers, which are referred to in here as cells, they'll all have a 0, which means it's a very low p-value. There is some relationship between each of these factors to metric A. And it looks like the number that's above is the Pearson correlation, which is the R value. And that's where we're going to see that there is, again, it looks like a strong relationship that each of these factors has to metric A. However, despite that, as we showed before in the matrix plot, we saw there is some relationship, though, between metrics C, D, and E as it's being compared over here. So we're validating that with now we have a p-value associated that there is some relationship. And again, the Pearson correlation that's being run here also looks like it seems to be a strong relationship. So again, based off of this information, we would say that metrics C, D, and E should be further examined to see if we need to exclude some of those because of some interdependency between them.
Now we'll begin step 4, where we'll run a multiple regression that creates variance inflation factors, or VIFs.
So again, now in step 4, we're going to be running a multiple regression, and we're going to generate the variance inflation factors, or VIFs, or sometimes called a VIFs. Well, the VIF calculates the degree of multicollinearity that you might see in one of the tested factors. So if you see a VIF that's greater than 10, then we say it would have high multicollinearity, but if it's between 5 and 10, it would have a moderate degree of multicollinearity. But if it's less than 5, then we would say that it has little, maybe no multicollinearity at all. So if we're running this test again in Minitab, we would go to the Stat menu, select Regression, and in the Options box you would select Variance Inflation Factors in order for those results to be displayed in the Output session window. So here's an example, again, if we run these same metrics here that we've been using so far, and this is where we've selected the VIF as part of our options that we want to view, and this is what we're looking for over here. So in this example, when we look at these, we would see that metrics D and E have a very high VIF. Again, anything over 10 is going to to be saying that there's some multicollinearity. And we kind of confirmed that from the last couple of tests, but this just validates it all the more. It's just another way for us to be confident when we say that there's something that needs to be examined between metrics C, D, and E, because it looks like there is some interrelationships between them. The data seems to be strongly confirming that for us. So just based off of this, you'll notice that metric C, though, is very low in its VIF. But even though it has a very low VIF, does not mean that we need to keep it and we need to exclude metrics D and E. It simply is the first one that was calculated in this list, where it didn't find any relationship with what was calculated up to that point, which would have been metric B. But at this point, now that we have metric D and metric E introduced in the equation, now it's calculated a high VIF. So this doesn't conclusively say metrics D and E are the ones we need to get rid of because they have a high VIF, but it does confirm to us there is some relationship here between them, some interdependency. And so we need to go back and re-examine that again, and just using a couple more steps here, and also with the validation of the team that would confirm whether which of these metrics we need to exclude if possible.
Okay, so for step 5, we'll reduce the factors to just those that are most critical and don't have any multicollinearity.
Well, now in step 5, we're going to try to reduce the factors to what we consider to be the most critical, that is, the ones that have the least amount or no multicollinearity, because that's what we're trying to do. Now, there are a couple ways we could do that. First method, we'll say method A, is a manual way of doing that. So we would say if there is a relationship that exists between the factors we're looking at, like we did in step 2, which was the matrix plot, as well as in step 3, which was the correlation that we ran, then what we can do is rerun the step 4, which is where we ran the regression with the VIF, and we can exclude one of those related factors one at a time, and we can continue to rerun that until we find that the VIFs are all less than 5. Well, that's one way to do it. But another way that might be a lot easier is to do a second method, which is called a stepwise analysis. And this is where we go in the mini tab, you go and select the stat menu and choose regression, and then select stepwise. Now from here, this is a test that will do all that automation for finding the ideal critical X factors for you. And as that way, it makes it a lot easier and much more effective for you to do the analysis to find out which ones are the most ideal that's going to give you the best level of results. So and what we're trying to do is we want to get our results that are logical, and we're going to get them validated by the team. So even though this might come up with some result that seems to be most ideal for us that we can select, we still have to make sure we validate that with the team, which is one of the last things we're going to look at. So just to see how the stepwise looks, what it looks like when we run that, again with all these same factors, here's the kind of output that we would see from Minitab. Well, based off of this, it's telling us again, here are the factors that we're looking at. Our response value, which is our Y, is metric A, and it's telling us that we've added 4 different predictors in there, and the number of values and observations we included within our data set. And then what we're first going to look for is the p-value for each of these. So you'll see that there's 4 actual combinations of these tests that it's running. So that's why it calls it stepwise, because it's stepping into multiple combinations of adding these factors in to give you the results to see how it's testing it. So in this first step right here, it's got metric A that's comparing with just metric E to give you those results. Step 2, it includes metric E, but then metric B as well, and gives you those results in that column. And then step 3, it's again metric A, metric E, and metric B, and now it adds in metric D, and so on. So it's purposely going out of order in here to select the best combination, and from the data that's output here, you and your team can choose which is the best combination that seems to most strongly indicate this is the transfer function or the factors that you need to identify as part of your transfer function. So within each of these, what you're going to look for, again, is the p-value that's associated with all these combinations. In this case, we're again looking for a small p-value, and here nearly all these are 0 except for this one when they consider metric C. It's still less than 5.05, but it's still much higher than the other ones. So that might give us a little bit of pause. It's still low enough risk, but barely just low enough. Now the next thing we need to look for also is looking at the R-squared adjusted value. We want to look for one that is high. Again, this shows what there's a relationship. So in this case, it's showing in all these combinations there's a very strong relationship that can be explained between each of these factors and the combination of the factors to that response, which is metric A. And next we're going to look for is the standard deviation. We want a standard deviation value that is low. The lower the standard deviation, the less variation that there is in the equation that we're going to be coming up with. So in this case, again, we want something that's much lower. And you can see for the first stepwise that's in here, accounting for just metric E, we still have a high R-squared adjusted, and the p-value for metric E is 0, but the standard deviation is about 3 times higher than some of the other combinations next to it. So it's something to consider as we go forward. And then finally, the fourth thing we're going to look at is the other value that's on the top for each of these metrics in the cells that are used in here. These are referring to the coefficients that are going to be used in a transfer function. So if we were to select one of these columns and use one of those as the combination for creating our transfer function, these values on top of each of these cells is really that coefficient that will be used as the multiplier within our transfer function. So if you look and see any that are very close to 0 as a coefficient or as a multiplier, what that's really doing is zeroing out that factor from the equation, almost indicating that we don't even need that factor at all. Just because, again, if you have a coefficient that is 0, you're zeroing out the result. It's not intended to be represented, so why even have it there in the first place? So in this case, you can see that metric C is one example where we have a very small coefficient. Multiplying this as a coefficient with metric C would in effect just zero out metric C, so there's probably no value in having metric C included into the equation in the first place. At least that's what we can probably conclude from these types of results.
Now in step 6, we'll evaluate the quality of the transfer function.
Alright, so now in step 6, this is we're going to evaluate the quality of the final transfer function we're trying to build. So we're going to try to build the transfer function and validate those factors with our team of what we're going to include or exclude. Now when we do this, we want to ensure that all the VIFs that we're looking for are less than 10 and if possible less than 5. We also want to ensure that the residuals that we're looking at from the analysis are independent and normally distributed, like it should be for any correlation test that we run and we look at those residuals. As well, we want to ensure that any outliers or unusual observations that might have occurred within our data set are validated by the team, or at least can be explained by the team. So we're going to go back to using that stepwise regression, and we're going to use that as our method for building the transfer function by pulling the constant and the coefficients from those equations. So this is the stepwise output that we saw before, and now based off of this is the transfer function that we could build from it. Again, so in order to build this, what we're looking at here is when we looked at the values that were available in the stepwise, there had 4 different combinations in here. So what we identified is this second combination is probably the one that would be the best for us to use. They had low p-values for each of the factors. R-squared adjusted was extremely high. As well, we had a very low standard deviation for it. So this might be the best. And again, it's very close to the one when we just have this first column, but the fact that the standard deviation is a little bit lower is a better thing for us. So in this case, this is why we might choose this example here. And because of that, that also means by only including metric A as our output Y and metric E and metric B as our X factors in the equation, that means metrics D and metric C can probably be excluded altogether because there's probably too much interdependency or multicollinearity between those factors and metric E, so we probably want to exclude them altogether. So in this case, if we say, all right, we're going to select this column for building our transfer function, here's what the ultimate transfer function might look like. And so we take the information that's from that column. Here's our constant that we would use. So we would have our metric A, which is our final output Y, is equal to this constant that's been identified for us. We plug that into building this equation. Then we add to that, again, metric E that we've identified here, plus its coefficient. So here's the plus the coefficient times our metric E. And then we're also going to add to that the coefficient that we're going to multiply by metric B as our final part of this building this equation.
Finally, in step 7 of these procedures, we'll assess the predictive capability of the transfer function.
Alright, now finally in step 7 as part of these procedures, we want to assess the predictive capability of this transfer function we've just built. This is really where the rubber meets the road for this transfer function so we can get some value out of it. We've worked so hard to get to this point. This is where we want to see, is this really going to be something meaningful to us, or at least to help us understand where we need to make certain changes and the effects of those different changes. So in order to run this part, we're going to go to the Stat menu within Minitab and select Regression, and then select Regression again. And the options box that's selected in there, we're going to add the prediction intervals to our test. So I'll show you how to answer that. But by doing this, by adding these prediction intervals, it's going to help us to answer the question, what would the output y be if we were to have a certain given input x's of certain values when we identify those? So in order to do this, we would have to type in values for those x factors, which would be our predictors. So here's what the combination would look like when we open up the regression box and we choose options. What we have selected in here is the response value, again, which is our primary y that we're looking at, and then we're only including now metric E and metric B, which we identified in our stepwise regression in the last step that we had, that these are the primary x's and inputs that we want to refer to. So then when we select options, this is the box that displays in here. And what we're going to do is we're going to type in the prediction intervals from over here. So if you notice, there are two sets of values, 500, and there's a space there that might be a little bit hard to see, but there's a space, then there's a 0.06. What this means is for these two columns of data that are provided in the worksheet of Minitab, then you have metric E and then next to it metric B. Well, that's the same order that you would type in your prediction intervals for that. So if we would say metric E, the value we're plugging in is 500. Then for metric B, then the value we're plugging in for that is 0.06 or 6%. So we're plugging in our prediction intervals into this part of the equation. And when we run this, it's going to create a certain output for us. And what we're going to examine is the predicted interval in the predicted values section of the predictive capability to see what that predictive capability is like for this transfer function. So this is the kind of output that we're going to see that comes out of this test. When we look at this, we're going to be looking for this portion here, the predicted interval. So this, when we interpret this, we're saying that we're 95% certain that metric A, which is our primary metric, again our output, will fall somewhere between 254.99 and 262.14 when we have a metric E at 500, which is what we plugged in, and metric B at 0.06 or 6%. Now we can run this equation in Excel if we wanted to. We actually didn't have to run the actual equation to see what it would be, but what's helpful for the predictive interval is it accounts for the 95% predictive interval, because if we ran the straight equation we get an exact result, but we also want to know that there's a 95% confidence level that we have here based off of only having a sample of 100 values in our test. So in that case we can't say we're going to have an exact result for the y, but we have some sort of range, this predictive interval. So when I say this is where the rubber meets the road, what I mean is that this is where it's really critical for us. What's the big deal for this? Well, the big deal is that if we are okay where this y is, let's say that we want to have our y falling within this range, and that's an acceptable range within the tolerance, that is like within our lower and upper spec limits defined by the VOC, or the voice of the customer. If that's what we want, then that means in order to achieve that, we have to have a metric E that's at the value of 500 and a metric B at 0.06. If we can achieve those levels of our x's and accomplish those, then we should be able to achieve a y that falls within that tolerance. However, if this is very difficult for us to achieve, a metric E at 500 or a metric B at 0.06, then that's what we need to work toward. Maybe it's acceptable for us to reach 500 for metric E, but maybe metric B, it's very difficult for us to have 0.06 or 6%. So if that's the case, that's where we need to target. We need to put our attention on trying to improve metric B, because that's the root cause. Let's fix metric B, get it to the point where we're at least sustaining a 0.06 value, again, whatever that means. But whatever that means and whatever we're trying to achieve, we want to at least achieve this value in order to get this type of predictive interval for our overall output. That's the point of this. It's a way for us to understand exactly where we can be if we set our values, our levers or our dials, if you will. In this case, for metric E, metric B, at a certain level, we can see what kind of predictive interval we can expect from our output Y. If this is not within a tolerable range, then we need to go back and figure out, well, what are the settings I need for metric E and metric B, and plug in those combinations in here. What is acceptable for what we can do now? What is possible for us? And with that, what kind of predictive interval does that give us? Well, if it's again not acceptable, then where do we need to be? Where do we need to make the improvements between these inputs in order to get us to the desired output?
Now, although it's not a formal step among these procedures, it's essential that after you run this, validate your results with your team.
Again, even though it's not an actual procedure within the multiple regression procedures that we've been evaluating, one of the most critical things we have to consider through this whole process is that we need to validate our results with our team that we're working with. So make sure we're going back to the team to review the findings and make sure that we're interpreting the results correctly, and really consider the team's opinion on this. You need to collaborate with them, because the team or any other supporting SMEs like subject matter experts that you're using as part of this process and interpreting the data and helping you to do the analysis on the data, they're your best validation of practical significance. Again, we can come up with whatever we want in the data, but if it's not practical, then we're missing the boat here. So we need to make sure that our team is in full agreement. So it's helpful to get the team updated regularly of the findings that you have along the way, and they can help steer and guide your analysis. So it's not something you go back into a room privately and figure out everything, but you need to go to your team on a regular basis, keep them informed. So that might mean having recurring meetings that you work with them to show them your findings, and they can give you better insight and clarity of where you need to guide your analysis or guide your interpretation, because you might be misinterpreting something. So you're not expected to take all this data, go into a back room and come up with some sort of silver bullet and some finding. That's not the point of this. You're not intended to be the mastermind. You're intended to be the one who facilitates and collaborates with the team of experts to figure out what the true root causes you're trying to solve. So if you're expected to go back and find a silver bullet, that's meaningless. A silver bullet is really only a paperweight unless you can make sure you're shooting that bullet at the right target. And that's where you need to work with your team. Let them help you and guide you in how you can accurately find, aim at, and hit the target root cause that you're trying to resolve in the first place.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to go back again to the output Y and those factors you identified as all through the analyze phase and doing the hypothesis testing, and run those through the multiple regression procedures that we've used in this exercise to test for multicollinearity that may exist within your data. And ask yourself, is there any multicollinearity that exists? And if so, how do you know it exists? So is the multicollinearity logical? That is, does it make sense to have it? Did you already know that there was some interdependency in those factors before you actually ran the test? And also, if it does exist, how would you modify your transfer function to account for that kind of multicollinearity?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.